Gravity might be the universe's greatest magic trick. We feel its pull every single day, and for over a century, we've believed Einstein's beautiful description of it as the curvature of spacetime. But what if that story, as elegant as it is completely wrong? A radical new idea is shaking the foundations of physics, suggesting gravity is not a fundamental force at all. It is an illusion, a side effect, a collective behavior emerging from something far stranger. This is the world of emergent gravity. By the end of this exploration, you will have toured 25 mind-bending theories that could completely rewrite the rules of reality. We are going to look under the hood of the cosmos, searching for the secret rulebook gravity has been hiding. What if the fabric of space is a hologram and dark matter is just a cosmic mirage? What if time itself is not fundamental, but something that crystallizes from timeless chaos? The journey ahead is not just about equations, it is about reimagining everything we think we know. Are you ready to question the very ground beneath your feet, or more accurately, the space that holds you to it? The first step into this strange new reality came from a Dutch physicist named Erik Verlinde. In 2010, he proposed something so radical it felt like pulling a thread that could unravel the entire tapestry of physics. He argued that gravity is not a fundamental force of nature. It is not woven into the fabric of spacetime itself. Instead, gravity is a side effect, a collective mirage that appears when you look at the universe in a certain way. It emerges. To understand this, think about the concept of temperature. You can touch a hot cup of coffee, but temperature is not a fundamental ingredient of the universe. It is a statistical property that arises from the frantic, collective motion of trillions of molecules. The molecules are real, but the warmth you feel is an emergent phenomenon. Verlinde proposed that gravity works the same way. What we perceive as the force of gravity is actually a consequence of something more fundamental: the information and entropy stored on the holographic boundary of space. Imagine the entire three-dimensional universe we live in is like a movie being projected from a two-dimensional screen that contains all the information about everything inside it. The interactions and changes on that screen, the shuffling of information bits, create the illusion of a gravitational force within the projected world. This was a breathtaking leap. It meant that the equations of gravity, even Einstein's sacred general relativity, were not the starting point. They were the end result, the thermodynamic equations of a deeper, information-based reality. The most stunning implication was for the mystery of dark matter. For decades, astronomers have watched galaxies spin too fast for the visible matter within them to hold them together. Something invisible, dark matter, must be providing extra gravity, but Verlinde's theory suggested a different answer. Perhaps there is no invisible particle at all. The extra gravitational effect we attribute to dark matter is just an apparent force, a discrepancy that naturally appears when you calculate gravity as an emergent phenomenon from the universe's information content. The physics world was electrified and deeply divided. Some hailed it as a visionary breakthrough, the first real step beyond Einstein in a century. Others were profoundly skeptical, questioning the mathematical rigor and whether the theory could make precise, testable predictions. But the genie was out of the bottle. Verlinde had opened a door, and through it, physicists began to see an entirely new landscape of possibilities. Verlinde's idea hinges on a concept so strange it sounds like science fiction, yet it is taken deadly seriously in theoretical physics. This is the holographic principle. To grasp it, we must start with the most mysterious objects in the cosmos, black holes. In the 1970s, physicists like Jacob Bekenstein and Stephen Hawking made a startling discovery. They found that a black hole has entropy, a measure of disorder or information content. But the truly bizarre part was where that entropy lived. It was not scattered throughout the black hole's vast interior volume. Instead, it was precisely proportional to the surface area of its event horizon, the point of no return. It was as if all the information about everything that ever fell into the black hole was not stored inside, but was painted, pixel by pixel, on its two-dimensional spherical surface. This was the seed of a revolutionary thought. What if this was not just a quirk of black holes? What if it was a fundamental law of the universe? The holographic principle boldly proposes that all the information needed to describe everything within any volume of space, every star, every planet, every person, can be fully encoded on the boundary of that space. Think of it this way: the rich, three-dimensional world you experience right now, with depth and solidity, might be like a breathtakingly realistic hologram. A hologram is a three-dimensional image created by shining a laser through a flat, two-dimensional photographic plate. The plate contains all the interference patterns, all the information necessary to project the illusion of a full three-dimensional object. In this cosmic analogy, our universe is the projected hologram. The true reality, the fundamental source code, exists on a distant, two-dimensional surface we can never see. Now, connect this directly to gravity. If our reality is a holographic projection, then the properties of that reality, including the force we call gravity, are not primary ingredients. They are secondary effects. They emerge from the interactions and processing of information on that fundamental boundary. The equations of gravity, in this view, are not the master laws. They are more like the equations of thermodynamics for a gas, describing large-scale behavior that arises from countless tiny, underlying events. The holographic principle transforms gravity from the architect of the universe into a kind of cosmic afterglow, a shadow cast by the true mechanics of information playing out on the edge of everything we know. The holographic principle gave us a stunning new metaphor, but it was a physicist named Ted Jacobson who provided the first concrete mathematical bridge. In 1995, long before Verlin's work made headlines, Jacobson performed a kind of conceptual magic trick. He started not with the majestic equations of general relativity, but with the humble, universal laws of heat. His key insight was deceptively simple. He proposed that every single point in the fabric of spacetime, if you could zoom in close enough, possesses a tiny amount of entropy. This entropy is not random. It is directly tied to the area of an unimaginably small patch of space surrounding that point. Think of the surface of a still pond. From a distance, it looks smooth and continuous, but up close, you see it is made of countless vibrating water molecules. Jacobson suggested spacetime is like that pond. Its smooth geometry is a large-scale illusion, and its microscopic molecules have a disorder, an entropy, that is fundamentally linked to surface area. From this single, profound assumption, Jacobson applied a bedrock law of thermodynamics called the Clausius relation. This principle states, in essence, that when you add a little bit of heat to a system, that heat is equal to the temperature of the system multiplied by the change in its entropy. It is a fundamental bookkeeping rule for energy. Jacobson applied this rule to the entropy of those tiny patches of spacetime. He asked, what happens when energy, in the form of matter or radiation, flows through one of these patches? That flow of energy is like adding heat. the entropy of the patch must change in response, and the Clausius relation tells us exactly how. Here is where the miracle occurred. When Jacobson worked through the mathematics of this thermodynamic process, enforcing the Clausius relation at every point in space, Einstein's field equations of general relativity emerged perfectly, as if from nowhere. Gravity was not the input, it was the output. His derivation showed that the force which shapes galaxies and bends starlight is not a fundamental interaction, but a collective, statistical behavior. It is the macroscopic law that emerges from the frantic, unseen activity of spacetime's own microscopic constituents, whatever they may be. To understand the scale of this shift, consider a flowing river. The science of fluid dynamics gives us powerful equations that predict whirlpools, currents, and waves. But those equations are not fundamental. They emerge from the chaotic interactions of trillions of water molecules. We do not need to track every single molecule to describe the river's flow. Jacobson's work suggested that Einstein's equations are the fluid dynamics of the cosmos. They beautifully describe the large-scale behavior of gravity, but they are themselves the emergent consequence of a deeper, more chaotic reality we have yet to fully see. He framed gravity not as geometry, but as thermodynamics, forever linking the fate of falling apples to the inevitable rise of entropy. Jacobson's work left us with a profound question. If gravity is the thermodynamics of spacetime, then what is spacetime made of? To find an answer, some physicists are looking not to the cosmos, but to the materials in our everyday world. This is the condensed matter analogy, and it proposes that the fabric of the universe might behave less like a smooth stage and more like a block of ice. Think about a crystal. At a macroscopic level, it is a solid, continuous object with specific properties, but zoom in to the atomic scale, and you see the truth. The crystal is not continuous at all. It is a lattice of discrete atoms arranged in a precise, repeating pattern. The solidity we experience is an emergent property of that underlying atomic structure. Now, apply that logic to spacetime itself. What if the smooth, four-dimensional continuum of space and time is an illusion that emerges from a vast network of discrete, fundamental building blocks? These would be the true atoms of reality, entities far smaller than any particle we have ever detected. In this view, the universe is not fundamentally smooth. It is granular, pixelated at the tiniest of scales, a concept often called the Planck length. Just as a digital photograph looks smooth from a distance but reveals individual pixels when magnified, spacetime may have a fundamental resolution. So, if spacetime has atoms, what are the particles of gravity? Here, the condensed matter analogy offers a beautiful parallel. Inside a crystal lattice, atoms are not static. They vibrate, and when they vibrate collectively in a coordinated wave, that wave travels through the material. We call that wave a phonon. It is not a fundamental particle like an electron. It is an emergent quasi-particle, a collective excitation of the entire atomic system. The theory suggests that gravitons, the hypothetical particles believed to transmit the force of gravity, might be exactly the same. They would not be fundamental ingredients of the universe. Instead, a graviton would be like a phonon of spacetime, a collective ripple in the network of its fundamental atoms. When this network vibrates in just the right way, the disturbance propagates, and we perceive that propagation as a gravitational wave. This shifts our entire perspective. We are not looking for a particle of gravity. We are listening for the distinctive hum of spacetime's underlying structure. But what could these spacetime atoms possibly be? One leading candidate comes from a theory called loop quantum gravity. It proposes that space is woven from tiny, one-dimensional loops, which intertwine to form a dynamic fabric called a spin network. The nodes of this network represent the smallest possible volumes of space, and the links between them represent areas. Another candidate is even more abstract. It suggests the fundamental entities are pure bits of quantum information, like the qubits in a quantum computer. The universe, in this view, is not a physical thing that computes, it is the computation itself. The dynamic relationships and entanglement between these information bits generate the illusion of geometry and gravity. This granular picture solves a major headache in physics. In Einstein's smooth spacetime, when you try to combine it with quantum mechanics, you get infinite, nonsensical answers. But if spacetime is made of discrete pieces, those infinities vanish. There is a smallest possible volume, a smallest possible area, so calculations do not blow up. The condensed matter approach does not just offer new particles, it offers a new origin story. Space, time, and gravity are not the starting point of creation. They are the phase of matter the universe settled into as it cooled from a formless, chaotic beginning. We are not living on a fundamental stage, we are living in a crystal that formed from something far more strange. But a network of information or loops still feels like a structure in space. What if space itself is not the foundation? Causal set theory makes a more radical claim. It suggests that the most fundamental ingredient of reality is not space or even spacetime, but something more primitive, causality. The theory proposes that the universe, at its heart, is nothing but a vast collection of discrete events. Think of these as the bare facts of reality, point-like happenings. The only thing that defines them is their relationship to each other, which events can influence which others. One event, like the striking of a match, can causally influence a later event, like the lighting of a candle. This web of cause and effect is the entire skeleton of existence. In this view, the smooth, continuous spacetime of our everyday experience is a secondary illusion, a large-scale approximation that emerges from the sheer density of these causal links. It is like a pointillist painting. Up close, you see only individual dots of color, disconnected and separate. But step back, and those dots blend into a smooth, continuous image of a landscape. The painting is not fundamentally smooth. The smoothness emerges from the collective pattern. Causal set theory says our four-dimensional reality is that emergent painting. The individual events are the dots, and the causal relationships between them create the illusion of a flowing, geometric continuum. So how do you build a universe from just cause and effect? Physicists use a process called sprinkling. Imagine taking a finite volume of spacetime, as described by Einstein's equations. Now, randomly sprinkle points into that volume, like tossing grains of sand into a box. Each grain represents a fundamental event. Then, you draw a line, a causal link, from one event to another if the first could possibly influence the second without traveling faster than light. This creates a vast, tangled web, a causal set. The stunning result is that if you start with a causal set built from such a random sprinkling into a classical spacetime, the large-scale properties of that original spacetime, its curvature and geometry, can be recovered just by studying the pattern of connections in the web. The smooth stage is not the input, it is the output. This turns the problem of quantum gravity on its head. Instead of trying to quantize spacetime, you start with a quantum theory of these discrete causal events. The dynamics, the rules for how the network grows and changes, would be governed by quantum principles. The hope is that from these simple, combinatorial rules, the familiar equations of general relativity would emerge naturally in the limit where you have a colossal number of events, just as the laws of thermodynamics emerge from the statistics of countless molecules. Gravity, in this picture, is not a force that bends a pre-existing stage. It is the perceived curvature that comes from the particular way the causal network is woven together. The fabric of reality is not a fabric at all, it is a story of cause and effect, and we are living within its plot. But if the universe is woven from a story of cause and effect, what is the story written on? The most minimalist answer possible is that it is written on nothing at all, just pure information. This leads us to a theory so elegant it borders on the philosophical. It is called it from qubit, and it proposes that everything we see, the entire physical universe, emerges from the entanglement of quantum bits. Imagine the most basic unit of reality is not a tiny string or a loop, but a binary choice, a quantum bit or qubit. This is not a particle in space, it is a fundamental unit of possibility, a 1 or a 0 that exists in a fuzzy superposition of both states until it is observed. Now, take a vast number of these abstract qubits and entangle them. Quantum entanglement is that famous spooky action at a distance, where two particles become linked so that measuring the state of one instantly determines the state of the other, no matter how far apart they are. In the it from qubit framework, this spooky connection is not just a curious feature of particles, it is the literal glue that builds space and time. The more two systems are entangled, the theory suggests, the closer they are in the emergent geometric space. Disentangle them, and the distance between them grows. This idea found its most dramatic expression in a conjecture with a cryptic name, ER equals EPR. It links two of Einstein's greatest insights, though he would have hated one of them. ER stands for the Einstein-Rosen bridge, better known as a wormhole, a hypothetical tunnel through spacetime connecting two distant points. EPR stands for Einstein-Podolsky-Rosen, the authors of a famous paper pointing out the bizarre implications of quantum entanglement, which Einstein dismissively called spooky. The conjecture, pioneered by physicists like Juan Maldacena and Leonard Susskind, boldly proposes that these two concepts are not just analogous, they are exactly the same thing. An entangled pair of particles, like two electrons created together and then flung to opposite sides of the galaxy, are not connected by some invisible signal. They are connected by a microscopic wormhole, a geometric bridge in the fabric of spacetime itself. The entanglement is the wormhole. This is a staggering unification. It means the weirdest phenomenon in quantum mechanics and the wildest concept in general relativity are two sides of the same coin. But how does this build a universe? Think of starting with a soup of qubits with no space between them, just pure quantum information. As these qubits become entangled in a vast, complex network, the connections start to define geometry. A dense web of entanglement in one region creates the illusion of a continuous, smooth volume of space. The rules of quantum information processing, how these bits interact and evolve, give rise to the dynamical laws of physics within that space, including gravity. In this view, gravity is not a force that acts across space. It is a force that emerges because space itself is a manifestation of quantum entanglement. When you try to pull two entangled particles apart, you are not fighting a force field. You are literally stretching the geometric connection, the microscopic wormhole, between them. This resistance to stretching is what we perceive as gravity. the theory offers a profound new origin for the fabric of reality. The universe began not with a bang in space, but with a fluctuation in a quantum computer of cosmic scale. Space, time, and matter crystallized as that initial state of information became increasingly complex and entangled. We are not living in a simulation, we are living inside the computation. The idea of a universe built from quantum information is elegant, but it still needs a blueprint. How does that abstract network of entangled qubits actually crystallize into the specific geometry we call spacetime? One theory provides a stunningly concrete answer, and its name is quantum gravity. Imagine the fundamental reality is not a smooth sheet, but a graph, like a vast, cosmic social network. Each point of reality is a node, and the connections between them are links. In the beginning, at energies so high we can barely conceive of them, this graph is complete. Every single node is connected to every other node. It is a featureless, buzzing hive of pure potential, with no sense of distance or direction. There is no space, because everything is equally connected to everything else. Then, the universe cools, just as water undergoes a dramatic phase transition when it freezes, shifting from a chaotic liquid to a structured crystal. The universe's fundamental graph undergoes its own cosmic freezing. Links between nodes do not simply vanish, they become fixed or they break. The all-to-all connections of the hot, early graph begin to thin out. As the temperature drops, a pattern emerges from the chaos. Certain connections strengthen and stabilize, forming a regular, low-energy structure. This new pattern of connections is not random. The surviving links define adjacency. Two nodes that remain strongly linked become neighbors in the emerging geometric space. The pattern of these neighborhoods, the way the graph is woven, dictates the geometry of spacetime itself. A region where the graph connections are dense and tightly woven might emerge as a volume of highly curved space, perhaps even the seed of a black hole. A region where the links form a regular, lattice-like pattern might become the flat, expansive vacuum of interstellar space. In this model, gravity is not a force that acts on this graph. Gravity is the graph, the perceived curvature of spacetime, which tells matter how to move, is a direct readout of the connectivity pattern of the underlying network. A massive object like a star would be a region of the graph with a specific, dense configuration of links, and the way this configuration influences the surrounding network's connectivity creates what we perceive as a gravitational well. The beauty of quantum gravity is how it demotes geometry from a fundamental stage to an emergent property, like the crystalline structure of ice. The ice did not exist before the water froze. The crystal emerged from the freezing process. In the same way, our four-dimensional spacetime did not exist before the universe cooled through its gravity phase transition. It solidified into being. This provides a radical new perspective on the Big Bang. The singularity might not have been a point of infinite density in space, but a moment of maximum connection in the graph, a state of perfect symmetry where no geometry existed at all. The birth of our universe was not an explosion in a void. It was the moment the cosmic graph began to freeze, crystallizing the first threads of space and time from a formless network of pure relation. The universe's graph froze into the geometry we know, but a glaring mystery remained etched across the sky. For decades, astronomers have watched galaxies spin with a defiant speed, their outer stars whirling so fast that the visible matter alone could never hold them together. The only explanation that seemed to fit was an invisible halo of dark matter, a mysterious particle that neither emits nor reflects light, providing the extra gravitational glue. But what if that glue is an illusion? This brings us to one of the most provocative ideas in emergent gravity, the theory that dark matter is not a substance at all, but a signature. It is an emergent effect, a cosmic mirage created because our equations for gravity are incomplete. Eric Verland's framework of entropic gravity provides the clearest path to this radical conclusion. Remember, in his view, gravity emerges from the information content on the holographic boundary of space. When you apply this emergent logic to a massive system like a galaxy, the calculations change in a profound way. The presence of ordinary matter, stars and gas, alters the entropy and information on that boundary. In the dense central regions of a galaxy, this is straightforward, and the emergent gravity matches Newton's and Einstein's predictions. But in the vast, sparse outskirts, a new effect kicks in. The long-range entanglement of quantum information across the holographic screen generates an extra contribution to the apparent force. From within the galaxy, this extra pull looks for all the world like it is coming from an unseen source of mass. It perfectly mimics the gravitational signature of a halo of dark matter, but there is no particle, no halo. The dark matter effect is simply how gravity behaves when it emerges from the deep quantum information of space. The evidence for this is written in the rotation curves of spiral galaxies. These are graphs that plot the orbital speed of stars against their distance from the galactic center. Under Newton's laws, stars farther out should orbit more slowly, just as Pluto moves slower than Mercury around the Sun. But in every galaxy we measure, the curve flattens. The outer stars orbit just as fast as the inner ones, as if gripped by an unseen hand. Particle dark matter models explain this by placing an immense, invisible sphere of matter around the galaxy. Emergent gravity achieves the same flattened curve through geometry alone, by deriving a new term in the law of gravity that becomes significant at galactic scales. The test, then, is in the details. Can emergent gravity explain other puzzles where dark matter is invoked, like the motions of galaxies within giant clusters, or the way massive clusters bend light from objects behind them, an effect called gravitational lensing? Early calculations by Verland and others suggest it can, and without the need to fine-tune the distribution of an invisible particle, the emergent picture makes a clean, testable prediction. The apparent dark matter effect should have a specific relationship to the ordinary matter present, because it is tied to that matter's entropy. It is not a separate, independent component that can be distributed arbitrarily. This is a fundamental philosophical shift. For particle dark matter, the universe is filled with two largely independent things, visible stuff and dark stuff, with one merely cloaking the other. For emergent gravity, there is only one thing, the visible universe, but its gravitational influence is more complex and far-reaching than we ever imagined because it is rooted in something deeper. The race is on. New telescopes are mapping the universe with unprecedented precision, measuring the distribution of mass through subtle warps in spacetime. They are looking for the telltale signatures that could distinguish a universe filled with invisible particles from one where gravity itself is an illusion emerging from the quantum void. The answer will not just solve a cosmic mystery, it will tell us whether we need to invent a new substance, or whether we have finally begun to read the hidden language of space. The connection between black holes and entropy is more than a curious fact, it is a direct window into the quantum heart of gravity. That window is the event horizon, the point of no return. In the 1970s, Jacob Bekenstein made a revolutionary proposal. He argued that a black hole's horizon must possess entropy, a measure of its hidden information. Stephen Hawking later solidified this, showing this entropy is not just some vague property, it is precisely quantified. The entropy of a black hole is proportional to the area of its event horizon. This is a bizarre and profound statement. In any other system, entropy is proportional to volume. The more space you have, the more ways you can arrange the molecules inside. But for a black hole, the entropy scales with its surface area. It is as if all the information about everything that ever fell into that cosmic pit is not stored in its vast interior, but is somehow compressed and painted onto its two-dimensional boundary. This area law for entropy was the first major clue that spacetime itself, at its most fundamental level, might be built from microscopic degrees of freedom that live on surfaces, not within volumes. The horizon is not just a barrier in space, it is an information screen. But what is the source of this entropy? The leading candidate is quantum entanglement. Imagine the vacuum of space not as pure emptiness, but as a seething quantum foam, with pairs of virtual particles constantly popping into and out of existence. Normally, these pairs annihilate almost instantly, but at the event horizon of a black hole, something dramatic can happen. One particle of the pair can fall inward, past the point of no return, while its entangled partner escapes outward, becoming real radiation. This is Hawking radiation. The process severs the quantum entanglement between the inside and the outside of the black hole. That severing, that loss of quantum connections, is what contributes to the black hole's entropy. The horizon marks the boundary where entanglement between interior and exterior is fundamentally disrupted. This suggests the entropy of the horizon is largely entanglement entropy, a measure of the quantum connections that have been cut. This idea turns geometry into a direct consequence of quantum information. If the entropy on a surface is entanglement entropy, then the very geometry of that surface, its curvature and gravitational field, might be dictated by the pattern and strength of the quantum entanglement across it. Experiments with theoretical models show something even more startling. If you manipulate the entanglement between two regions of space, say by carefully adding or subtracting quantum correlations, the equations suggest the emergent geometry between those regions changes in response. Increase the entanglement, and the space appears to contract or warp. Decrease it, and the space seems to stretch. This is not magic, it is mathematics pointing to a deep truth. Gravity, the force that shapes spacetime, appears to be an entropic force driven by the tendency of quantum entanglement to maximize itself. The black hole's horizon, the ultimate entropy machine, is not an anomaly. It is the clearest example of a universal principle, that where information is stored and how it is entangled, literally weaves the fabric of reality we call space. Black holes show us the quantum threads of reality, but what about the very first moments of everything? The standard story of the Big Bang runs into a profound wall of ignorance, a singularity where all known laws of physics break down. Emergent gravity offers a breathtaking escape route, suggesting the Big Bang was not a beginning in time, but a beginning of time. It was a cosmic phase transition, the moment the universe crystallized from a formless, pre-geometric state into the structured spacetime we recognize. This radically reshapes our understanding of the universe's most dramatic growth spurt, the epoch known as inflation. In the Standard Model, inflation is a process that happens within an already existing, rapidly expanding spacetime. A mysterious field, the inflaton, provides a burst of repulsive gravity, stretching the universe exponentially in a fraction of a second. But from the emergent perspective, this story puts the cart before the horse. How can a process of spacetime expansion occur before spacetime has fully solidified? The emergent proposal flips the script entirely. Inflation might not be a process within spacetime, but the process of spacetime emerging. Imagine the pre-geometric phase as a hot, buzzing, and highly connected quantum graph or a dense soup of entangled qubits. This state is unstable, like supercooled water desperate to freeze. As it begins to cool, it undergoes a rapid, cascading phase transition. The connections in the graph start to lock into a stable pattern, or the quantum entanglement spreads and organizes. This locking and organizing is not happening in space, it is creating space. The exponential expansion we call inflation is not the stretching of a fabric, but the explosive crystallization of that fabric from a microscopic seed. The driving force is not a mysterious field with repulsive gravity, but the thermodynamic urge of the system to settle into a lower entropy, geometric state. This solves the singularity problem elegantly. There is no point of infinite density because there was no pre-existing volume for matter to be crammed into. The universe did not start small, it started non-spatial. The transition to geometry created both space and the energy that filled it in one unified process. Within this churning emergence, the seeds of all future structure were planted. In the standard model, quantum fluctuations in the inflattened field get stretched to cosmic scales, becoming the density variations that later grew into galaxies. In the emergent model, the source is different, but the outcome is similar. The crystallization of spacetime would not be perfectly smooth. As the graph freezes or the entanglement network forms, there would be quantum fluctuations in the process itself. Some regions might crystallize slightly faster, others slightly slower, creating tiny variations in the emergent geometry and energy density. These primordial wrinkles, imprinted on spacetime as it was being born, would then be the templates for everything to come. The vast cosmic web of galaxies and voids we see today could be a frozen record of the quantum jitter that accompanied the universe's transition from a formless state to a geometric one. This reframes our entire cosmic history. We are not living in the aftermath of an explosion in a void. We are living inside a crystal that formed from a more fundamental and utterly alien state of reality. The force of gravity that shaped this crystal was not there at the start, guiding the process. It was the process, the thermodynamic signature of spacetime solidifying into being. This crystallization of spacetime from a formless state suggests a remarkable new character for gravity itself. Perhaps it is not a force, but a fluid. One of the most powerful mathematical discoveries in emergent gravity is a principle known as the fluid-gravity correspondence. It reveals a stunning duality, a perfect mathematical mirror, between the equations of Einstein's gravity in a particular kind of curved space and the equations that describe the flow of a viscous, strange fluid. This special space is called anti-de Sitter space. Unlike our own universe, which appears to be expanding, anti-de Sitter space is negatively curved and static, like the interior of a giant cosmic bowl. The correspondence states that a theory of gravity in the volume of this bowl is exactly equivalent to a theory of fluid dynamics living on its boundary, its rim. It is the holographic principle in its most precise, calculable form. The entire churning, geometric interior, with its black holes and gravitational waves, is encoded in the ripples and flows of a fluid on the edge. This is not just a vague analogy. Physicists can take a complex problem in fluid dynamics, like the chaotic swirl of a turbulent flow, and translate it directly into a problem about gravity in the curved interior. Solving the gravity problem, which might be mathematically simpler in that exotic space, then gives you the answer to the original fluid problem. The fluid on the boundary has specific, measurable properties. It has viscosity, a resistance to flow, it has entropy, and the correspondence provides exact formulas linking these fluid properties to fundamental gravitational quantities. For instance, a famous result shows that the ratio of a black hole's entropy to its viscosity, calculated from the gravity side, yields a precise number that also characterizes the fluid's ability to transport momentum. This is a smoking gun for emergence. Fluids are the classic example of an emergent phenomenon. No single water molecule is wet or has viscosity. Those properties arise only from the collective, statistical dance of countless molecules. The fluid gravity correspondence tells us that gravity, in this precise mathematical setting, behaves exactly like such a fluid. The curvature of spacetime, the force that bends light, emerges from the collective behavior of whatever fundamental degrees of freedom live on the boundary, just as the flow of a river emerges from the motion of its water molecules. The gravitational field is not a fundamental entity, it is the thermodynamic description of a deeper, microscopic system. When you shake this cosmic fluid, the disturbances propagate as gravitational waves. When you heat it up in a region, you might create a black hole, analogous to a vortex or a singularity in the flow. This perspective transforms our vocabulary. We no longer just say a black hole has entropy. We can say it has a temperature and a viscosity. Spacetime itself has a kind of texture and resistance. The force of gravity becomes less about geometry and more about hydrodynamics, the science of flow. While our universe is not exactly an anti-de Sitter space, the power of this correspondence is undeniable. It provides a concrete, working model where gravity is undeniably emergent, a fluid, dynamic phenomenon written in the language of geometry. It suggests that searching for a quantum particle of gravity might be as misguided as searching for a single molecule of water that embodies the concept of a whirlpool. The whirlpool is real, but it is a pattern of the whole, not a piece of it. The fluid analogy gives us a powerful picture, but it still assumes a stage, a background geometry for the fluid to flow upon. To go deeper, we must question the stage itself. What if the very coordinates of space and time, the labels we use to map reality, break down at the most fundamental level? This is the realm of non-commutative geometry, a theory that proposes spacetime is not just pixelated, but fundamentally fuzzy. In our everyday world, the order in which you do things does not always matter. If you walk 5 steps north, then 5 steps east, you end up in the same spot as if you walked 5 steps east first, then 5 steps north. The coordinates commute. They are interchangeable. This common sense rule is the bedrock of our smooth, classical picture of space, but in the quantum realm, this bedrock crumbles. For subatomic particles, the order of operations is everything. Measuring a particle's position first and its momentum second gives a different result than measuring momentum first and position second. This is the famous Heisenberg uncertainty principle, and mathematically, it is expressed by saying the position and momentum operators do not commute. Non-commutative geometry applies this quantum logic directly to the fabric of spacetime. It suggests that at the unimaginably tiny Planck scale, the coordinates of space themselves become quantum operators that do not commute. What does this mean in practice? It means that if you could probe a region of space the size of a Planck length, the very concepts of here and there, before and after, lose their sharp meaning. The notion of a point in spacetime dissolves into a kind of quantum foam, a probabilistic haze where geometry is inherently uncertain and non-local. There is a fundamental fuzziness woven into reality's foundation. Yet, miraculously, from this chaotic, non-commutative algebra, our familiar, smooth world emerges, just as the chaotic jostling of air molecules averages out to give us a clear, predictable concept of atmospheric pressure. The wild quantum fluctuations of spacetime coordinates average out when we zoom out to human or cosmic scales. The non-commutative relations smooth over, and the coordinates begin to commute once more. In this low-energy, large-distance limit, the fuzzy quantum foam crystallizes into the continuous, classical stage of general relativity. The equations of Einstein's gravity emerge not as fundamental laws, but as the statistical thermodynamics of this underlying, non-commutative geometry. This framework does more than just generate gravity, however. It offers a breathtakingly elegant path toward unification. The mathematics of non-commutative geometry naturally provides extra dimensions, not as curled-up loops of space, but as abstract, internal dimensions described by algebra. These internal dimensions are not places you could travel. They are mathematical spaces that encode the properties of particles and forces. Within this structure, the gravitational field and the fields of the standard model of particle physics, like the electromagnetic and nuclear forces, find a common mathematical home. They all arise from different aspects of the same non-commutative geometry. In this view, the photon, the gluon, and the graviton are not separate messengers of separate forces. They are different vibrational modes, different expressions of the same fundamental fuzzy geometry. The force that holds atoms together and the force that holds planets in orbit would share a single geometric origin, emerging together as the universe cooled and the coordinates of reality settled into their classical, commuting order. This paints a universe where the distinction between force and geometry, between matter and the stage it plays upon, is an illusion of scale. At the heart of everything lies not a particle, not a string, but a mathematical melody where the notes, the coordinates of existence, do not play in a fixed order, creating the rich, coherent symphony of spacetime and substance we perceive. A universe built from fuzzy coordinates suggests a deeper structure still waiting to be decoded. One of the most mathematically audacious ideas in this search proposes that the fundamental ingredients of reality are not particles, not even strings, but vast, abstract arrays of numbers called matrices. This is the world of large N-matrix models, where the N represents an unimaginably large number, and from this sea of pure mathematics, spacetime itself is meant to crystallize. Think of a matrix as a spreadsheet, a grid filled with numbers that can interact and multiply according to specific rules. Now, imagine not one, but a whole collection of these infinite spreadsheets, each one a matrix, all dancing and interacting with one another in a complex, quantum mechanical ballet. In the limit where the number of matrices and their size, n, becomes infinitely large, something miraculous is theorized to happen. The chaotic, collective oscillations of these matrices can reorganize themselves, and from their patterns, the familiar concepts of space, time, and even gravity are born. It is a bit like understanding a crystal. If you could write down the complete quantum mechanical description of every atom in a lattice of salt, you would have an impossibly complex set of equations. But when you step back and look at the whole, new properties emerge, like the crystal's transparency, its hardness, its specific shape. Those properties were not in the individual atoms, they are collective behaviors of the system. In the matrix model proposal, our four-dimensional spacetime continuum, along with the gravitational field that curves it, is that emergent crystal. The individual matrix elements are the atoms, and the smooth geometry we experience is the large-scale structure that forms when a near-infinite number of them lock into a stable pattern. The connection to string theory here is profound. One specific matrix model, known as the Banks-Fischler-Schenker-Susskind, or BFSS model, provides a direct link. In certain limits, the dynamics of these interacting matrices are exactly equivalent to the dynamics of strings and the higher dimensional objects called D-branes. A D-brane can be thought of as a membrane of various dimensions where strings can end. In this matrix description, the matrices themselves are the D-branes. The off-diagonal elements of the matrices correspond to open strings stretching between different branes, and their interactions describe how these strings move and vibrate. So, where is the space in all this? The matrices' eigenvalues, which are a set of special numbers associated with each matrix, are interpreted as the spatial coordinates of the D-branes. As these matrices evolve and their eigenvalues spread out, they literally paint a picture of a spatial geometry. The distances between objects in this emergent space are not fundamental. They are derived from the relations between these matrix numbers. Gravity enters the picture as a force that also condenses out of this matrix soup. When the matrices are in a highly excited, hot state, their complex interactions can produce configurations that correspond to black holes within the emergent spacetime. The gravitational attraction between emergent objects is not a separate force added to the model. It is a consequence of how the matrix degrees of freedom interact and entangle with one another. This is a universe where physics is not happening in space. Space is what happens when physics reaches a certain scale and complexity. The theory makes a staggering prediction that in its most fundamental description, our universe has no dimensionality at all. There are no preconceived notions of up or down, past or future. There are only matrices and the rules for their interaction. The three dimensions of space and one of time are low-energy illusions, a particular stable state that the matrix system fell into as it cooled from a more symmetric, hot beginning. So the next time you look at the night sky, consider a radical possibility: the vast distances between stars, the curvature of spacetime around a planet, the very stage upon which the cosmic drama plays out, might all be the grand and beautiful echo of an infinite matrix solving its own equation. But a universe built from pure mathematics must still confront its most baffling observation. The cosmos is not just expanding, it is accelerating, driven by a mysterious, repulsive force known as dark energy. This acceleration is quantified by a single number in Einstein's equations, the cosmological constant. Yet this tiny number presents physics with its most embarrassing failure: the cosmological constant problem. The vacuum of space, according to quantum field theory, should be a seething ocean of energy. Every quantum fluctuation contributes a little bit, and when you add it all up, the predicted vacuum energy density is a number so monstrously large it should have ripped the universe apart in an instant, over 120 orders of magnitude stronger than what we actually observe. This is not just a minor error, it is the worst theoretical prediction in the history of science. Emergent gravity offers a radical way out by suggesting the cosmological constant is not a fixed parameter of fundamental law, but an integration constant that emerges dynamically. In standard physics, the cosmological constant is a term you plug into the equations from the start, a fundamental feature of reality's blueprint. But in an emergent framework, it could be more like the water level in a lake. The water level is not a property of individual water molecules. It is a global condition that arises from the total amount of water and the shape of the basin. Similarly, the cosmological constant might not be an input, but an output, a global property of the universe that settles to a specific value based on the total information content and the boundary conditions of the holographic screen. This changes the fine-tuning problem from a cosmic mystery to a question of equilibrium. Why is the vacuum energy we observe so small? Perhaps because a universe with a large, positive cosmological constant is inherently unstable or unlikely to form complex structures like us. In some emergent models, the effective vacuum energy is tied directly to the amount of information that can be stored on the cosmic horizon. As the universe expands, that horizon grows and the information capacity changes. This dynamic link could allow the apparent cosmological constant to adjust over cosmic time, naturally trending toward the small value we measure today without impossible fine-tuning. Dark energy, in this view, is not a strange substance filling space. It is the thermodynamic pressure of the universe's information boundary, a holographic effect of the vacuum's quantum entanglement. The accelerating expansion we witness might be the universe naturally relaxing toward a state of maximal entropy, where the information on the horizon and the energy within reach a stable balance. This reframes our cosmic destiny. The fate of the universe may not be written in a fundamental constant, but is an unfolding story written in the language of emergent information, a story where the very stage of reality adjusts its own tension as the plot unfolds. Dark energy's challenge pushes us to consider a more direct modification of gravity's own nature. What if the messenger of gravity, the graviton, is not massless after all? This is the world of massive gravity, a bold theoretical departure where the graviton is given a tiny but non-zero mass. In Einstein's general relativity, the graviton must be massless to ensure the force has an infinite range, like light. But if the graviton has even a minuscule mass, gravity's reach becomes finite. It would weaken over immense distances in a specific way, potentially mimicking the effects of cosmic acceleration without any dark energy. For decades, constructing a consistent theory of massive gravity was a nightmare. Early attempts, like the work of Fears and Pauli, were plagued by ghostly instabilities, mathematical pathologies that rendered the theories nonsensical. The breakthrough came with the de Rham-Gabadad's Tolle theory, often called DRGT massive gravity. It tamed the ghosts through a clever mathematical structure, providing the first consistent classical framework for a massive graviton. But how does this connect to emergence? The DRGT theory can be beautifully reinterpreted not as a fundamental theory of a massive particle, but as gravity emerging from a condensate. Imagine a universe filled with a kind of invisible, all-pervasive fluid made of scalar fields. These fields have a value at every point in space, like a temperature or a pressure. Under the right conditions, these fields can undergo a phase transition and condense, much like water vapor condensing into liquid. This condensate spontaneously breaks the symmetry of spacetime, giving the graviton an effective mass. The process is deeply analogous to the famous Higgs mechanism in particle physics. In the Standard Model, the Higgs field condenses throughout space, and particles like the W and Z bosons wade through this cosmic treacle, acquiring mass as they interact with it. In the gravitational Higgs mechanism, It is the graviton itself that gains mass by interacting with a background condensate of scalar fields. The geometry of spacetime is no longer the sole player. It couples to this fixed background structure. This reframes massive gravity as an emergent phenomenon. The force we feel is not a fundamental interaction with a massive messenger, but an effective force that arises from the dynamics of this cosmic condensate. The condensate provides a preferred reference frame, a kind of subtle lattice against which spacetime's vibrations, the gravitons, must move. This modifies their propagation, making them behave as if they have mass. The cosmological implications are profound. A massive graviton changes the long-range behavior of gravity. On solar system scales, the effects are negligible, preserving all our successful tests of Einstein's theory. But on the scale of the entire visible universe, the force could naturally weaken. The accelerating expansion we attribute to dark energy might simply be gravity fading at the largest distances, a direct consequence of its messenger particle having a tiny mass. This offers an elegant alternative, replacing a mysterious dark energy with a specific modification to gravity's own character, one that itself emerges from a deeper, condensate state of the cosmos. The challenge now is to find observational signatures that could distinguish a universe with a massive graviton from one with a cosmological constant. Subtle differences in the way gravitational waves propagate over billions of light years, or precise measurements of how galaxy clusters grow, might one day reveal if gravity's messenger has been hiding a secret mass all along. Giving the graviton mass introduces a subtle background, a whisper of a preferred frame, but our universe, as far as we can measure, screams of perfect symmetry. This is the principle of local Lorentz invariance, the bedrock of Einstein's special relativity. It states that the laws of physics are the same for all observers moving at constant velocity, and there is no preferred state of rest. Light always travels at the same speed, no matter how fast you chase it. This symmetry is woven so deeply into reality that any emergent theory of spacetime faces a monumental challenge. If space is built from a discrete network, a graph, or a causal set, that underlying structure is like a crystal lattice, and a crystal has a preferred orientation, breaking rotational symmetry. How then does our smooth, isotropic universe, with no preferred direction, arise from such a granular foundation? This is the puzzle of emergent local Lorentz invariance, and its solution is one of the most elegant tricks in the emergent gravity playbook. The key is that Lorentz symmetry is not exact at all scales, but becomes an excellent approximation at the low energies and long distances of our everyday world. Think of a fluid, like air or water. At the molecular level, it is a chaotic mess of atoms colliding in a lattice or random directions. There is no perfect symmetry at that scale. But when you zoom out to the human scale, all that microscopic chaos averages out. The fluid appears perfectly isotropic, the same in all directions. Sound waves travel through it at a fixed speed regardless of the direction you face. The symmetry of fluid dynamics emerges from the statistical behavior of the underlying disorder. Causal set theory achieves this through its random sprinkling of events. Remember, a causal set is built by randomly placing points into a volume of classical spacetime. This randomness is crucial. Because the sprinkling is random, there is no regular, crystalline grid to pick out a special direction. On average, over a large enough region containing many events, the causal links point in all directions equally. The discrete, underlying structure becomes invisible to long wavelength probes, like the particles and light we use to measure the universe. What remains is the statistical illusion of a continuous, Lorentz symmetric spacetime. The symmetry is not built in, it is washed in by the sheer number of random elements. Quantum gravity uses a different, dynamic mechanism. In its hot, early phase, the graph is completely connected, a featureless state with maximum symmetry. As it cools and the links break to form a lattice-like structure, it does not freeze into a single, static crystal. Instead, the pattern of broken links can vary from place to place, forming a kind of random mosaic. To a low-energy observer using long-wavelength light, this mosaic appears smooth and uniform. Any potential violation of Lorentz symmetry, like light traveling at slightly different speeds in different directions, would be a microscopic effect. Its signals would be suppressed by the incredibly high energy scale of the graph's structure, far beyond what any particle accelerator could ever probe. So, the constancy of the speed of light is not a fundamental decree. It is a collective phenomenon, a consensus reached by the universe's fundamental constituents when viewed from our low-energy, macroscopic perspective. The stage of reality is not perfectly crafted, it is statistically flawless. This resolves a deep tension. It shows how a universe built from discrete, non-geometric parts can still perfectly mimic the continuous, symmetric stage demanded by a century of precise experiments. The symmetry we hold sacred is not a property of the building blocks, but a property of the crowd. This flawless symmetry of our stage brings us to a far more intimate mystery, the very flow of the play itself. In our quest to unify gravity with quantum mechanics, physicists have stumbled upon a chilling and profound puzzle. When you write down the most fundamental equations of quantum gravity, time vanishes. It simply is not there. The Wheeler-DeWitt equation, a cornerstone of quantum cosmology, describes a static universe of possibilities, a frozen snapshot where nothing happens. This is the problem of time, and it suggests that our most visceral experience, the relentless march from past to future, might be the grandest illusion of all. Emergent gravity proposes a radical answer. Time is not a fundamental dimension. It is a story that the universe tells itself, emerging from the changing relationships between things that are themselves timeless. One elegant proposal is the Page-Wouters mechanism. Imagine the entire universe as a single, static quantum state. Within that frozen hole, you can identify a subsystem to act as a clock, like the position of a hand on a cosmic dial. The rest of the universe, including you and me, becomes the system to be observed. Time emerges not because the universal state changes, but because the correlations between the clock and the observed system change. When the clock reads one value, the observed universe is in one configuration. When the clock reads another, the universe appears to have evolved. There is no external time ticking away, only the relative ticking of one part of the quantum whole against another. We are not watching a movie projected on a screen of time. We are inside a single, complex frame where different pixels are correlated in a way that creates the sensation of a sequence. But this raises another question. Why does this emergent time only flow forward? Our lives are a one-way street from memory to anticipation, from cause to effect. This is the arrow of time, and its origin may be thermodynamic, deeply tied to the concept of entanglement entropy we have seen before. Recall that black holes have entropy proportional to their horizon area, an entropy linked to quantum entanglement. The universe as a whole may follow a similar rule. As the universe expands and evolves, the the total quantum entanglement between different regions increases. This growth of entanglement entropy provides a direction. The state of the universe moves from a past of lower entanglement to a future of higher entanglement. Our psychological arrow of time, our memory of the past but not the future, could be a direct consequence of this cosmic trend. We remember the past because it was a state of lower entanglement, and the increase in entanglement as we move forward creates the irreversible processes that define our experience, from the shattering of a glass to the fading of a star. The flow you feel, the relentless push of now, might be the universe entangling itself into an ever more complex and connected whole. In this view, gravity is not just emerging from a timeless structure, it is part of the engine that drives the emergence of time itself. The curvature of space and the flow of time are two faces of the same emergent phenomenon, both arising from the universe's deep need to tell a story with a beginning, a middle, and an end written in the language of quantum information. The timeless flow of quantum information must eventually meet the hard light of experiment. For all its philosophical elegance, emergent gravity stands or falls on one simple question: can we test it? The answer is a resounding yes, and the hunt is already underway across scales, from the vastness of galaxies to the quiet of a laboratory bench. At the galactic scale, the prime battleground remains the mystery of dark matter. Teams of astronomers are now conducting precision comparisons, pitting the predictions of Eric Verlin's emergent gravity directly against those of the particle dark matter model. Their tools are exquisitely sensitive. One is weak gravitational lensing. This is the subtle warping of light from distant galaxies as it passes through the gravitational field of a nearer galaxy cluster. By mapping these tiny, statistical distortions, astronomers can reconstruct the distribution of mass in the cluster, creating a gravitational map. The key difference lies in the pattern. Particle dark matter predicts a specific, smooth halo of invisible mass surrounding the visible galaxies. Emergent gravity predicts the apparent extra mass is tied directly to the visible matter's own distribution and entropy, creating a slightly different lensing signature. Early studies have shown intriguing matches to Verlin's predictions without needing dark matter, but the results are not yet conclusive. The other critical test is the detailed shape of galaxy rotation curves. While both theories can produce flat curves, they predict different relationships between a galaxy's stellar mass, its gas content, and the precise orbital speeds of stars at every radius. New surveys like the European Space Agency's Euclid mission are measuring millions of galaxies with unprecedented detail, searching for these telltale fingerprints in the data. The universe is essentially running the same experiment over and over again, and we are finally gathering the statistics to read the result. But the search is not confined to the heavens. If spacetime has a fundamental graininess, a discrete structure at the Planck scale, could we ever hope to detect it here on Earth? Ingenious tabletop experiments are trying to do just that by looking for subtle signatures of modified inertia or quantum spacetime foam. One approach uses ultra-precise interferometers, even more sensitive than those that detected gravitational waves. The idea is that if spacetime is not a smooth continuum, but a frothy, quantum foam, a particle traveling through it would experience a slight, random jitter in its path. Over very long distances or very sensitive measurements, this jitter could manifest as a tiny, fundamental noise in the system, a whisper of the universe's pixelated resolution. Other experiments probe the possibility that inertia, an object's resistance to acceleration, might not be a fundamental property, but could be modified by the universe's information content, as suggested by some emergent frameworks. By measuring the acceleration of supercooled, microscopic test masses with phenomenal accuracy, physicists hope to see a deviation from Newton's second law at extremely small scales or accelerations. These lab-based quests are long shots, requiring us to detect effects from a scale a billion times smaller than an atom, but they represent a direct assault on the smooth stage of classical physics. Finally, the grandest test of all looks at the entire cosmos. The afterglow of the Big Bang, the cosmic microwave background, is a frozen snapshot of the infant universe. Its minute temperature fluctuations are a blueprint for all the structure that followed. Cosmologists run massive computer simulations to see which initial conditions grow into the galaxy clusters and cosmic web we see today. The simulations that include cold dark matter particles match the observed large-scale structure spectacularly well. This is the strongest evidence for the particle model. The challenge for emergent gravity is to produce simulations that start from its own principles, perhaps with a dynamic, information-based origin for the initial fluctuations, and see if they can match the exquisite detail of the cosmic microwave background and the distribution of galaxies across billions of light-years with equal or better success. Similarly, the accelerating expansion driven by dark energy leaves distinct imprints on how clusters of galaxies form over cosmic time. An emergent explanation where the cosmological constant is dynamic or gravity weakens on large scales would predict a different history of structure formation. By combining data from the cosmic microwave background, galaxy surveys, and supernova distances, scientists are constructing a multi-pronged test that no theory can easily evade. The verdict is not in, but the trial has begun. Every new telescope, every deep space map, and every quiet experiment in a vault brings us closer to answering whether gravity is a fundamental force of nature or the universe's most convincing magic trick. But for all its promise, emergent gravity faces a storm of skepticism from the heart of mainstream physics. The most pointed criticism is a question of scientific integrity, falsifiability. A good theory must make clear, risky predictions that could prove it wrong. Critics argue that some versions of emergent gravity, especially the broad philosophical framework, are too flexible. They can be adjusted after the fact to fit new data, rather than making bold, specific forecasts that telescopes can confirm or deny. If a theory can explain anything, it ultimately explains nothing. Proponents counter that the core ideas, like Verlin's specific formulas for galaxy rotation without dark matter, make precise numerical predictions that are absolutely testable and are being tested right now. The debate hinges on whether emergent gravity is a single, sharp theory or a fertile but vague paradigm still waiting for its definitive mathematical form. A more technical, but equally serious, challenge lies in the classical limit. For emergent gravity to be correct, it must perfectly reproduce every single validated prediction of Einstein's general relativity in the regimes we have already tested, from the orbit of Mercury to the bending of light around the Sun, and the precise timing of signals from GPS satellites. Recovering the full, intricate machinery of Einstein's equations from a deeper information-based principle is an immense mathematical hurdle, while successes like Jacobson's thermodynamic derivation are groundbreaking, showing that the broad outline of the equations can emerge. The devil is in the details. Critics want to see every term, every constant, every subtle effect emerge naturally and uniquely from the underlying model, not just the general form. It is one thing to show that a theory produces something that looks like gravity. It is another to show it produces exactly the gravity we have measured for a century, with no adjustable knobs. Then there is the quantum problem. The Holy Grail is not just an emergent theory of classical gravity, but a complete theory of quantum gravity. How do you build a quantum version of a theory where spacetime itself is not fundamental? This is a profound technical maze. In most emergent approaches, you must first define the fundamental quantum degrees of freedom, be they entangled qubits, causal set elements, or matrix variables. Then you must show that their collective quantum dynamics produce an effective field theory that, at low energies, not only looks like classical general relativity, but also includes its expected quantum corrections. This is a staggering task that no emergent model has yet fully accomplished. String theory and loop quantum gravity have spent decades building their quantum frameworks. Emergent gravity must now build its own from the ground up, and the construction is only just beginning. Perhaps the strongest empirical counterargument comes from the cosmic crime scene of the bullet cluster. This is a system of two colliding galaxy clusters. Observations show that the bulk of the visible matter, in the form of hot X-ray emitting gas, was slowed by friction during the collision and lies in the center. But the gravitational mass, mapped by gravitational lensing, has sailed right through and now resides in two distinct clumps far from the gas. For particle dark matter advocates, this is a smoking gun. Dark matter particles, they argue, would barely interact with each other or the gas, so during a collision, the dark matter halos would pass through each other unimpeded, just where the lensing map shows the mass to be. They say no modification of gravity alone can explain this separation, because gravity in a modified theory should still be tied to the visible mass, which is the gas stuck in the middle. Emergent gravity theorists are not conceding. They propose that the emergent apparent dark matter effect is not tied solely to the local visible matter, but to the entropy displacement of the entire system. In a violent event like a cluster collision, the entropy distribution and the resulting emergent gravity could become displaced from the gas, potentially mimicking the observed separation. It is a complex calculation, and the debate over this single object encapsulates the entire struggle, a tug of war between an invisible substance and a recalibration of the force itself. The path forward is not in dismissing these criticisms, but in confronting them head-on, for they are the whetstone against which any revolutionary idea must be sharpened. The battle over the bullet cluster highlights the high stakes of this scientific revolution, but it is part of a much larger war for the soul of reality itself. For decades, two titanic frameworks have dominated the quest to unite gravity with quantum mechanics, string theory and loop quantum gravity. Emergent gravity is not a third contender trying to topple them. It is more like a secret bridge, revealing that these seemingly rival approaches might be describing the same profound truth from different angles. String theory, in its most popular conception, portrays the fundamental ingredients of reality as unimaginably tiny, vibrating strings. But its most profound insight is not about strings, it is about holography. The anti-de Sitter space conformal field theory correspondence, or AD-SCFT, is the full mathematical realization of the holographic principle we discussed earlier. It is the precise dictionary that translates a theory of gravity in a bulk volume into a quantum field theory living on its boundary without gravity. This is not an analogy, it is a proven mathematical duality. In this framework, gravity in the interior is undeniably emergent. It is a collective, thermodynamic phenomenon that crystallizes from the complex, quantum interactions of particles on the boundary. The force that bends spacetime is literally built from the entanglement of those boundary degrees of freedom. So, while string theory often gets presented as a theory of everything built from tiny strings, its greatest gift to emergent gravity is this concrete proof that a geometric, gravitational universe can be a holographic projection. Loop quantum gravity takes a starkly different path. It does not invoke extra dimensions or holographic boundaries as a starting point. Instead, it directly quantizes the fabric of spacetime itself. In this theory, space is not smooth. It is woven from a dynamic network of one-dimensional loops, forming a structure called a spin network. The nodes of this network represent the tiniest possible volumes of space, and the links represent the areas between them. This is a universe built from pure geometry, but a geometry that is granular and quantum. When this spin network evolves over time, it creates a four-dimensional structure known as a spin foam, a frothy, ever-changing tapestry of spacetime events. Here is where the connection to emergence becomes beautifully clear. While loop quantum gravity begins with quantized geometry, the large-scale, smooth spacetime of general relativity must emerge from the collective behavior of this spin foam. The continuous stage we experience is not fundamental. It is the classical limit of a vast quantum network. In this sense, loop quantum gravity is inherently an emergent theory of geometry. The spin foam is the underlying, pre-geometric substance, and the curvature of spacetime is a statistical property that appears when you zoom out. So, are these two giants competing or complementary? They start from opposite shores. String theory, through AD-SCFT, says geometry and gravity emerge from a non-gravitational quantum system on a boundary. It is top-down, from the boundary to the bulk. Loop quantum gravity says geometry is fundamental but discrete, and smooth spacetime emerges from the quantum dynamics of its atoms. It is bottom-up, from the quanta to the continuum, yet both arrive at the same breathtaking conclusion: the spacetime of our daily lives is not the bedrock of reality. It is a phase, a stable configuration that forms under the conditions we live in. Some physicists dream of a grand synthesis. Perhaps the spin networks of loop quantum gravity are the microscopic description of the holographic screen in string theory. Maybe the entangled qubits of the it from qubit program are the true constituents of the spin foam. The quest is no longer about which single picture is correct, but about understanding the translation manual between them. Each framework is like a different map of the same uncharted territory, one drawn in the language of strings and holograms, the other in the language of loops and volumes. Emergent gravity is the compass pointing toward their convergence, the idea that wherever the true fundamental theory lies, it will not contain gravity or spacetime as we know them. They will be the magnificent, inevitable consequence. This convergence points toward a truth far stranger than any single theory. If gravity is not a fundamental force, but an emergent phenomenon, then we are forced to confront a staggering philosophical question. What then is real? For centuries, physics has largely operated under a substantivalist view. This sees spacetime as a real, substantial entity, an absolute stage upon which the drama of particles and forces plays out. Einstein himself wrestled with this, as his equations described the stage as dynamic and flexible, but still a stage. Emergent gravity shatters this stage entirely. It champions a relationalist view. In this picture, spacetime is not a thing. It is a web of relationships, a network of connections between events. What is fundamental are not points in a pre-existing void, but the causal links, the entanglements, the information exchanges between things. Distance and duration are not measured against a background grid. They are derived from the strength and pattern of these relationships. Two atoms are not close because they occupy nearby points on a map. They are close because they are intensely entangled, sharing a vast amount of quantum information. The map is not the territory, the relationships are the territory. This flips our entire conception of reality. It suggests the universe is not made of stuff located in space, but that space itself is made from the stuff of connection. The solidity of the world around us, the vast distances between stars, the unidirectional flow of time, all become a persistent illusion generated by an inconceivably dense network of underlying relations. This naturally leads to an even more radical proposition, that the cosmos is fundamentally informational or even computational. The true bedrock of reality might not be energy or matter, but bits, qubits, the yes or no answers to quantum questions. In this view, particles, forces, and even the laws of physics are not the source code. They are the user interface, a high-level, emergent dashboard that our conscious minds have evolved to interpret. The universe does not compute, it is the computation, the dynamic updating of quantum information according to simple, perhaps even logical, rules generates the rich, geometric tapestry we mistake for fundamental reality. Gravity, in this framework, is not a force in the program. It is a feature of the operating system, a consequence of how information is stored, processed, and entangled across the cosmic network. This radically alters our understanding of physical law. The equations we worship, from Newton to Einstein, are not eternal truths etched into the universe's foundation. They are effective bylaws, the statistical rules of thumb that emerge in our particular cosmic epoch, much like the laws of thermodynamics emerge from molecular chaos. They are incredibly reliable and powerful, but they are not primary. This reshapes causality and locality at their core. In a relational, informational universe, what does it mean for one event to cause another? Causality may itself be an emergent concept, a story we tell about the consistent ordering of events in the emergent timeline, and locality, the idea that objects are only influenced by their immediate surroundings, dissolves. If space is made from entanglement, then what is immediate? Two particles on opposite sides of a galaxy can be more fundamentally connected, more local in the network of relations, than two dust grains sitting on your desk. The spooky action of quantum entanglement is not spooky. It is a direct glimpse into the relational wiring beneath the geometric illusion. To accept that gravity is emergent is to accept that we have been reading the universe's user manual, mistaking the beautifully designed interface for the unfathomable hardware running beneath it. The user manual of reality might be written in a language we are only beginning to understand, the language of computation. This brings us to one of the most extreme visions of emergence, the idea that the universe is not just like a computer, it is a computer. In digital physics, the cosmos is not made of particles and fields in a continuous space. It is made of information and the rules for processing it. Reality is a vast, ongoing computation, and everything we perceive, including gravity, is an output of the program. Think of the simplest possible digital system, a cellular automaton. Imagine a grid of squares, each one either black or white. You start with an initial pattern, then apply a simple rule to every square based on the colors of its neighbors. For example, a rule might say, if a square has two black neighbors, turn it black, otherwise turn it white. You apply this rule over and over, updating the entire grid at each tick of a cosmic clock. From these mind-numbingly simple, local rules, astonishingly complex and beautiful patterns can emerge, swirling and evolving in ways that seem to have a life of their own. The physicist and computer scientist Stephen Wolfram has argued that our universe might be just such a cellular automaton, but operating on a hyperdimensional grid. The intricate laws of physics, from quantum mechanics to general relativity, would not be fundamental. They would be the large-scale, statistical patterns that emerge from the relentless application of these simple, digital rules. In this view, a particle like an electron is not a tiny ball. It is a persistent, stable pattern in the cellular automaton, a specific configuration of bits that maintains its structure as the rules update. A gravitational field would be another kind of pattern, a curvature in the way information propagates across the grid. When two of these particle patterns interact, the computational rules governing their intersection might create the illusion of an attractive force, a pull that emerges purely from information dynamics. This is digital philosophy taken to its logical conclusion, pioneered by thinkers like Edward Fredkin. He proposed that the ultimate stuff of reality is not matter or energy, but bits. Every event, every particle collision, every photon of light is the result of a cosmic computer evaluating a logic gate. The universe is not just computational, it is literally a digital computer, and the laws of physics are the software it is running. This leads to the provocative and often misunderstood simulation hypothesis. If our universe is fundamentally computational, then it is logically possible that it is being run on a substrate outside of itself, a cosmic computer built in a higher dimensional reality. While this sounds like science fiction, it forces a profound question about emergence. If we are in a simulation, then gravity is doubly emergent. First, it emerges from the computational rules of the simulation's code, the way the program handles mass and energy. Second, that entire simulated universe, with its emergent gravity, is itself an emergent phenomenon within the hardware of the simulating computer. The key insight from digital physics is not whether we are in a simulation, but that computation might be the fundamental process from which physics arises. Gravity, then, would be a force that emerges from the way information is processed and updated across the network. When a star warps spacetime, it is not bending a fabric, it is altering the rules of information flow in its region of the cosmic processor. The pull you feel standing on Earth is not a fundamental interaction. It is the computational consequence of your pattern interacting with the planet's pattern within the program. This reframes the search for a theory of everything. We are not looking for a single, elegant equation. We are looking for the shortest program that can generate our universe as its output. The quest becomes one of finding the minimal set of rules, the most compact algorithm that, when run, produces all the complexity we see, from the stability of atoms to the expansion of galaxies. It suggests that at the base of reality lies not a law, but a rule, and from that rule, everything else, even the stage upon which it all plays, is an emergent story written in bits. A universe built from pure computation invites us to strip reality down to its barest bones. One of the most powerful tools in physics is to simplify a problem until its core mechanics shine through, and for gravity, that means traveling to a world of profound simplicity. Imagine a cosmos not of 3 spatial dimensions, but just 2. This is the realm of 2 + 1 gravity, a universe with 2 dimensions of space and 1 of time, like the surface of an infinitely large sheet of paper where time flows. Studying this stripped-down model has provided some of the clearest mathematical proof that gravity can be an emergent illusion. In our familiar 3 plus 1-dimensional universe, Einstein's equations describe a dynamic, rippling geometry. Mass and energy tell spacetime how to curve, and that curvature tells objects how to move. A crucial feature is the existence of gravitational waves, ripples in spacetime that carry energy and information across the cosmos. These waves represent local degrees of freedom, meaning the gravitational field can hold energy and vibrate in complex ways at every point. But in a 2 plus 1-dimensional world, something remarkable happens. General relativity becomes empty at every local point. There are no gravitational waves. There is no local curvature that is not directly tied to a matter source. If you take all the matter away, the spacetime that remains is perfectly flat, not just approximately, but exactly. It has no local dynamics of its own. The theory becomes topological. What does topological mean here? It means the physics does not care about the precise distances or angles, the detailed geometry of the space. It only cares about the global shape, the overall connectivity, like whether the universe is shaped like a flat plane, a sphere, or a donut. The force of gravity in such a world is not about a local pull. It is entirely about the global structure of the universe. This simplification is not a bug, it is a feature. It turns an impossibly complex problem into a manageable one, a perfect laboratory to test how spacetime and gravity could emerge from something more fundamental. In this clean, topological sandbox, physicists have constructed explicit models where the smooth geometry of the 2 plus 1-dimensional universe unambiguously emerges from a theory that makes no mention of geometry at all. One of the most successful approaches uses what are called topological quantum field theories. These are quantum theories whose observables are immune to tiny, continuous deformations of spacetime. They depend only on the global topology. The Chern-Simons theory is a prime example. In this framework, gravity in 2 plus 1 dimensions can be exactly described as a Chern-Simons theory. The fundamental variables are not metrics or curvatures, but abstract connections living on the spacetime manifold. The amazing result is that the classical geometry of spacetime, with its Einstein equations, emerges as a kind of collective, classical shadow of this deeper quantum connection theory. Even more concretely, scientists have shown how this emergent spacetime can arise from models of interacting spins on a lattice, much like the quantum gravity idea, but in this simpler dimension. You start with a network of quantum mechanical spins, like tiny magnets that can point up or down, arranged on a disordered web. The interactions between neighboring spins are governed by specific rules. As the system cools or reaches a certain energy, these spins can spontaneously align in a pattern that is no longer just a magnet. The excitations, the disturbances in this aligned spin sea, behave exactly like particles moving in a continuous, two-dimensional space. The geometry of that space, and even an effective gravitational force between those particle-like excitations, is dictated entirely by the pattern of entanglement and interaction in the original spin system. The stage is not assumed, it is generated. The profound lesson from this flatland universe is a proof of principle. It demonstrates, with mathematical rigor, that a theory with no inherent notion of distance or curvature can give birth to a world that has both, complete with laws that look just like Einstein's gravity in that dimension. It shows that the degrees of freedom we associate with gravity, the ability to wave and curve, can be collective excitations of a system whose true variables are something else entirely, like quantum connections or spins. For our richer, more complicated 3 plus 1-dimensional home, the task is vastly harder because our gravity has those local, dynamic degrees of freedom, the gravitational waves. But the 2 plus 1-dimensional success is a guiding light. It tells us that the emergence of geometry is not a pipe dream. It is a mathematical reality in a simpler world. The challenge is to find the correct, more complex precursor in our own universe, whose collective behavior produces not just a static stage, but a dynamic, vibrating spacetime filled with the force we call gravity. Flatland's clarity proves the concept, but our universe is a roaring, 4-dimensional symphony. So where do we go from here? The frontier of emergent gravity is now a race on 3 parallel tracks, each one aiming to transform a brilliant metaphor into a concrete, predictive science. The first and most urgent track is the quest for a precise, mathematically rigorous emergent gravity theorem. Right now, the field is rich with compelling ideas, but critics rightly demand a single, unified framework. Physicists are working to distill the common principles from holography, entanglement, and thermodynamics into a set of fundamental postulates. The goal is a theorem as robust as Einstein's derivation of relativity from the constancy of light speed. It would state, unequivocally, that given a quantum system with certain universal properties, like a high degree of entanglement and specific information processing rules, a classical geometric force that obeys Einstein's equations must emerge. This is not about finding one more model, it is about proving a necessity, showing that gravity is an inescapable consequence of a deeper quantum reality, much like pressure is an inescapable consequence of moving molecules. The second track dives into the heart of that deeper reality, searching for the universal microscopic mechanism. What is the true atoms of spacetime that generate everything? Is it a spin network, a causal set, a matrix model, or something entirely unforeseen? The dream is to identify a single, simple set of quantum building blocks and interaction rules that, when you step back, produce not just gravity, but the entire zoo of particles and forces in one emergent sweep. This is the hunt for a theory where both gravity and quantum mechanics are twin siblings, born from the same parent process. In this vision, the weirdness of quantum superposition and the curvature of spacetime would be different faces of the same underlying phenomenon, finally ending a century of separation. The final track is where theory meets the unforgiving light of data, and here we are entering a golden age. New astronomical observatories are coming online that will test these ideas with breathtaking precision. The Vera Rubin Observatory, with its gargantuan camera, will map billions of galaxies, measuring their shapes, rotations, and distributions in unprecedented detail. It will provide a cosmic census so vast that subtle deviations from particle dark matter predictions, the kind emergent gravity might produce, will be impossible to hide. Simultaneously, gravitational wave astronomy is moving beyond mere detection into a phase of precision listening. Observatories like LIGO, Virgo, and the future space-based LISA mission will catch the ripples from colliding black holes and neutron stars across the universe. By studying the exact way these waves propagate, scientists can search for signs that spacetime has a subtle graininess or that gravitons have a tiny mass, both potential hallmarks of an emergent origin. Every chirp and ringdown from a cosmic collision is a direct probe of gravity's nature. And then there is the most speculative yet thrilling possibility of all. If gravity truly emerges from a manipulable structure, like a network of quantum information, could we one day learn to influence it? This is not about anti-gravity devices, but something far more profound. It suggests that the fabric of reality might have a substrate we could, in principle, interact with. In the distant future, understanding spacetime as an emergent phenomenon could lead to technologies as unimaginable to us as a smartphone would be to Newton. Perhaps we could engineer materials with exotic gravitational responses, or develop quantum computers that simulate spacetime itself, allowing us to experiment with the laws of physics in ways nature never intended. The ultimate promise of emergent gravity is not just a new equation in a textbook. It is the potential to see the universe not as a finished sculpture, but as a living process, and in that vision, we might find the keys to a deeper kind of understanding, one that blurs the line between observing the cosmos and participating in its very construction. The final frontier of this journey asks a question that echoes back to the very beginning of physics. If gravity is an illusion emerging from deeper laws, then what about everything else? The other fundamental forces, electromagnetism and the nuclear forces, have always been treated as separate, fundamental interactions, described by the flawless equations of the Standard Model. But in a universe built from information, could they be illusions too? The most ambitious theories of emergent gravity dare to propose exactly that, envisioning a world where all forces, and even the particles themselves, are unified as different facets of a single, simple origin. This grand vision rests on a concept known as emergent gauge symmetry. In particle physics, a gauge symmetry is a mathematical principle that underlies each force. For electromagnetism, it is the symmetry that allows us to change the definition of an electron's phase at every point in space without affecting any observable outcome. This symmetry demands the existence of a force carrier, the photon, to maintain consistency. Traditionally, this symmetry is put into the theory by hand, a fundamental rule of the game. But what if the symmetry itself is not fundamental? What if it, like spacetime, emerges from the collective behavior of something simpler? Think of it like the phenomenon of sound in a crystal. The atoms in the lattice have no inherent concept of a sound wave, but their collective vibrations create phonons, which behave like particles. More profoundly, these vibrations exhibit symmetries and conservation laws that were not present in the individual atoms. The symmetry emerges with the collective mode. In an analogous way, some physicists propose that the gauge symmetries of the Standard Model are like the symmetries of sound. They are not written into the universe's source code. They arise as stable, persistent patterns in a vast sea of more fundamental quantum bits or relationships. One promising path uses the language of entanglement we have already seen. Just as the geometry of space might emerge from the pattern of entanglement between regions, the electromagnetic field could emerge from the pattern of entanglement between different types of quantum information. Imagine each fundamental site in the network, each atom of spacetime, can hold not just one bit but several. The way these internal bits are entangled with the bits at neighboring sites could create what looks, on a large scale, like a field of force. A specific, swirling pattern of entanglement might correspond to an electric field, while a different, twisting pattern might correspond to a magnetic field. The photon would then be an emergent particle, a collective ripple in this entangled tapestry, just as the graviton is a ripple in the geometry. In this picture, an electron is not a fundamental dot. It is a topological defect, a kind of persistent knot or twist in the entanglement pattern. and its electric charge is a measure of how this knot interacts with the surrounding electromagnetic tapestry. This framework points toward a staggering unification. If both gravity and the other forces emerge from the same substrate of quantum information, then they were never truly separate. They are different vibrational modes of the same cosmic system, like different notes played on a single instrument. The force that holds your atoms together and the force that holds you to the planet share a common, deeper ancestry in the logic of quantum connections. The dream is to start with a vast, formless array of qubits governed by a single, simple rule for interaction and entanglement. As this system cools and settles, different patterns condense out. One large-scale, coherent pattern becomes the geometric fabric of spacetime and gives us gravity. Other, more intricate patterns become the gauge fields that give us light and nuclear forces. The particles of matter become stable excitations, like solitons or defects, within these combined patterns. Some of the most advanced mathematical work in this direction comes from string theory's holographic principle. In the AD-SCFT correspondence, a theory of gravity in the bulk is equivalent to a quantum field theory without gravity on the boundary. But that boundary theory is not arbitrary. It often looks remarkably like a gauge theory similar to those in the Standard Model. This provides a concrete, albeit exotic, example where gauge forces and gravity are two descriptions of the same underlying reality. They are unified because they are literally the same thing seen from different perspectives. The challenge is to move this beautiful duality from the special arena of anti-de Sitter space to our own accelerating universe. If this vision proves true, it would represent the ultimate simplification of physics. We would not have a theory of everything that is a long, complicated equation combining gravity and quantum fields. Instead, we would have a theory of almost nothing, a sparse set of rules for whatever the fundamental, pre-geometric degrees of freedom are. From that minimalist starting point, the entire rich panorama of our universe, with its four forces and myriad particles, would crystallize through a cascade of emergent phenomena. The laws we have painstakingly discovered over centuries would be revealed as the inevitable, statistical bylaws of a deeper order. The search for a unified force would end, not with a grand equation, but with the realization that all forces are stories we tell about the same magnificent, underlying process. So we have ventured through a cosmos where gravity is not a force, but a story. We have traced the thread from the holographic screen to the quantum graph, from the fluid of spacetime to the timeless network of cause and effect. 25 theories, each a different path through the same breathtaking landscape, all pointing toward a single, radical truth. Gravity may not be a fundamental ingredient of the universe. It is an illusion, a magnificent collective behavior emerging from something far stranger and more profound. We have seen gravity reborn as thermodynamics, as the pressure of quantum entanglement, as the crystallization of information from chaos. The stage of space and time is not the foundation, but the grandest performance, a show written in the language of entropy and played out on the boundary of everything. This journey redefines not just a force, but our entire conception of reality. It suggests that the cosmos is not a collection of things in a void, but a tapestry of relationships. We are not passive observers on a fixed stage. We are patterns within the weave, our very sense of place and time woven from the same quantum threads. What does this mean for the future of physics? It is an invitation to think bigger, to look beyond the equations we have mastered and ask what they are hiding. The quest is no longer just to find a particle of gravity, but to decipher the source code of existence itself, to read the universe not as a finished book, but as a living computation. It is a humbling and exhilarating prospect. The ground beneath your feet feels solid. The planets move in predictable arcs, but beneath that familiar order lies a deeper, wilder reality waiting to be understood. Which of these 25 visions resonates most with you? Does the holographic universe feel like the answer, or does the idea of a cosmic graph freezing into being capture your imagination? Share your favorite theory in the comments below and let us know what cosmic mystery we should explore next. If you enjoyed this deep dive into the fabric of reality, be sure to subscribe. We are just getting started, and there are countless more secrets waiting in the dark between the stars.